All right, guys. I am working my way back from break here. We do, if you haven't looked at the schedule yet, you'll notice that we have 2 weeks of actual, class, and then we have our exams. I mean, it's almost Christmas already, which is just crazy how fast that comes. But probably the best time of year. I know it's my favorite time of year. Hopefully yours. I mean, if not, that's fine. You can have other favorite times of the year, but we do have some work to do, though. We have 2 weeks of working on this unit on radicals, and then we do have our exams. So we do need to get some work done before Christmas break. So what I have up here is a little warm-up. I just kind of wrote down some perfect squares, perfect cubes, perfect fours. I highly, 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 highly recommend that you write down these numbers, these terms, and not that you have to memorize them, but I want you to be familiar with a bunch of them. As you see like that 625, and, if you're dealing with a perfect force or something like that, and you're like, wait, I remember seeing a 625 somewhere. I know that's one of those numbers that we can simplify. I just want you to kind of get used to that. And then also write down these parts of a radical. I'm going to kind of start there in just a second. I want to give you a chance to pause the video and then kind of go from there. So give yourself a second to write this down, pause the video, and once you're caught up, hit play again. Okay, so first off, the parts of a radical, I have them named here, and it is important to kind of know some of these names, but it's okay if you don't sometimes. It's more about what these things do and what they mean. But before I talk about that, I want to remind you of the types of functions we've dealt with up to this point. So we've dealt only with 2 types of functions so far. The first type is your absolute value functions. So that's the first one. And that's your y equals absolute value of x and things like that. The second type, which really encompasses every other function we've done, are going to be polynomials. And, you remember a polynomial can be like y equals 2, y equals x, y equals x squared, x cubed, and so on. And we've dealt really, when we're dealing with lines, we're dealing with polynomials. We deal with quadratic functions. That's a degree 2 polynomial. So everything has really been under the same umbrella, really, especially with domain. Domain's been all real numbers for everything. Well, that's going to change. We're going to get into all that as we kind of delve deeper into this unit. But for right now, understand that we're in a new type of function. So there's going to be some new rules. Some of the things that have always worked may not work as we move forward, so be aware of that. But let's talk about those radicals. So what a radical really is, it's not actually this little guy. I mean, this is a radical. I mean, I should say that, that it's not. But this is what a radical really looks like. Its basic form looks like this. And this is going to be very important to what we're doing today. So make sure we're writing this down. So it's going to be y equals a to the m over n. That's what a radical is. And what that means is this term on the top, this is going to be your power, and the number on the bottom is going to be your root. If you go back here and you look, the root that I have written here, it has another name, which can be your index, but you'll normally see it written as a root. So I like to call it a root because it makes more sense that way. But there's no power written in here. So you want to say, where's this m coming? Well, the m comes right here. This is your m. That's your power. It's the power of the radicand, or the term inside the radical, whatever power it's to. So what you do is you take that, and you can write it as a fractional exponent. Now, one thing polynomials don't have is they don't have fractional exponents. They have whole number exponents. It's either x to the first, or x to the second, or x to the third, or so on. It is not x to the 3/2, or x to the 1/2, or whatever fractions we could get. So that's why we're delving into a new type of function. So again, this y equals a to the m over n becomes this. Becomes the nth root of a to the m power. These mean the exact same thing. Again, these two things I have written down are exactly the same thing. They're just written in a different format. Okay, that's going to be very important to know as we get into our simplifying with variables. Okay, now one thing you've probably already dealt with is square roots, and I want you to be aware that you may not be used to seeing these numbers here, because if there's no index or no root, it is assumed that that root is 2. That would represent a square root. That is the given. Like normally if I have x by itself, it's a given that there's a 1 in front of it, and it's a given that that power is 1. Those things are given. Well, with radicals, it's a given that your root or your index is a 2. You may say, well, why don't we say or assume that that index is a 1? I'll give you one quick example. So if I had the square root of x and I said that's 1, then I don't have a fractional exponent. I have a power of 1 and a root of 1. The whole reason why we have a radical is to represent a fractional exponent. So if I made this a 1, I don't have a fraction, which means why do I even write this radical? So again, you will never see a radical with a root of 1. Otherwise, it's not a fractional exponent, which means why am I writing a radical to begin with? It would make no sense. So you have to have a fraction denominator of anything other than 1. Otherwise, we have a whole number for a power, because anything over 1 is a whole number, any positive number, I should say. So that's why we say it's a given that it's a 2 to start, because that would give you a fraction, like 1/2, 3 halves, 4 halves, 5 halves. Now, some of them simplify to give you whole numbers, but again, that's where your givens begin. So if there's no index, it is assumed that it's 2, in other words, it's a square root. So as I start simplifying here, you'll see that number right there is a 2. So anyway, now that we know that, I want to write this as the square root of 4 over the square root of 25. This would be the one that hopefully you're familiar with, because we've done square roots in Algebra 1. So the square root of 4 is 2, and the square root of 25 is 5. Again, if you know those perfect squares, that makes this a lot easier. And that's why I said it's nice to have that little chart up above so you can kind of get an idea of what those should be. All right, next up, we got our cube roots. So now we have to figure out what do I need to multiply 3 times to get 125. Well, first off, be aware that there's a negative in front. Now you may think, hey, I got a negative, I have an I term. But again, let's look at it this way. Not necessarily. So I'm going to have now the cube root, and we want to break this up into 3 numbers, all of which multiply to give me 125. Well, if you think about it, and again, this is more kind of still like a warm-up here. I'm trying to give you some leeway, or I'm trying to help you out. So this would be -5 times -5 times -5. I broke this up into 3 terms. Notice, yeah, there's some negatives in here, but when you multiply negative 3 times, you get a negative, which means I don't have an I as part of my answer because this is a cube root and not a square root. So this actually simplifies. This is the cube root of -5 to the 3rd power. Notice the power and the root are the same. So if you divided them, this would be to the 3 over 3 or -5 to the 1st. So your answer is -5. Notice I was able to pull that negative out. There's a lot of ways to simplify that radical, and that's where sometimes people get confused in this unit because they feel like there's got to be one way to solve this, and they have to do it the way I did it. You don't. You really don't. There's a ton of different ways to get to these. It just depends on how you mess with the numbers. So, and I'll try to show you that on some of these, but that's how I did this one. So that's how I'm doing it. But the next one here, we got a 4th root. So now we have to do the exact same thing. I got to figure out, okay, and first off, I'm going to write it like this: 4th root of 81 and the 4th root of 16. This is a good example to show you, hey, if you wrote these charts up here already, you'll realize, wait, these numbers are perfect fourths. So I don't have to go through all this work. Like 81 is right here, and 16 is right there. And if you see that, you can realize, oh, that's 3 to the 4th and 2 to the 4th. So this is just going to be 3 to the 4th, so that's 3. That's the cube root. Maybe I should write out that work so I don't confuse anybody. So this would be the fourth root of 3 to the 4th power. And again, if you can get the power and the root to match, it's basically 3 to the 1st power, because 4 over 4 is 1. All right. Next up, I have the 4th root of 2 to the 6th, or 2 to the 4th. And again, the power and the root match, so I get 2. Because again, 2 to the 4 over 4 is 2 to the 1st. And there we go. So that's just going to be 3 halves. So that's just some simple simplifying radicals for you. And now, just to kind of give you some idea, I was dealing with these negatives now, and I noticed I didn't have that I in there. I want to talk about that real quick. So I'm going to go through this chart super fast. So first off, you have an even index or an even root, and we have a positive radicand, so like the square root of 4, or the square root of 9, or the 4th root of 81, we're going to get a real answer from that. We're going to get a real number. And the number of possible roots that we could get are 2, because we could have plus or minus depending on the situation. If it's an odd radical, and we still have a positive root, we still get a real number. That still happens. Obviously, we have a positive radical. But we're only going to get one answer from that one. However, and this is where the weird thing came up, what about if I have an odd root and a negative radicand? Well, notice when I solve this, I got a real number. So be aware of that. If you have an odd power with a negative radical inside, we're going to get a real number from it. And we're going to get one possible solution. So the only time we're going to get imaginary numbers is in this situation, which is the one that's starred because it's different. Okay, this has different sets of rules. This is where you get imaginary roots. You have an even radical, like a square root, which is the only one we've dealt with so far, and a negative radicand. That's where we pull that negative out and we get I. So we have that imaginary number. You still get your 2 possible roots, plus or minus, as you solve it. So this is going to be all your different scenarios. So that's the only scenario where we get imaginary numbers. Okay, now you may notice I didn't put the plus or minus on the examples up here. It does say give all possible roots, so I probably should, but I want to kind of remind you of the different scenarios, and I'll actually add this in. So if I'm asking you, if I'm giving you a radical, because I didn't read my own directions, I said find all possible, so you'll see what I'm talking about, why I didn't have them written before. I just didn't read my own directions. But these should be plus or minus when you're doing an even radical. If you remember that whole process, you're simplifying radicals. But this guy is not plus or minus, because positive 5 times positive 5 times positive 5 is not negative 125. So you see how that's only one answer. Down here, however, if you multiply 3 halves, or really think of 3 and 2 separately, you know, if I multiply a negative 3 4 times, I'm going to get a positive. If I multiply negative 2 4 times, I'm going to get a positive. So this is plus or minus as well. So I have plus or minus 3 halves. But the only reason why I wasn't writing it before, but I needed to read directions, if I'm giving you a radical, like here, I'm just saying simplify the radical. I'm not saying anything, you know, special. Then if this is a positive radical and it's given to you as a positive, then your answer is going to be positive. However, if I say find all possible roots, then that's when you use your plus or minus. So again, if I am just saying here's the radical, and I just say simplify, I'm not being specific, then you're going to assume that I want the positive one, unless I say specifically I want all the answers. Now, the ones we've dealt with so far have been stuff like this, like x squared equals 4. If I say solve it, I'm literally just saying, hey, square root this and give me all the answers. Well, in this case, I did the square root as part of solving the problem. So I need both answers. Both answers will solve that equation. But here's the scenario I'm dealing with now. I'm just saying, hey, what's the square root of 4? Well, because I'm saying, if I'm not being specific,